Hello and welcome. Today is Friday, August 21st. Tomorrow we have the NVIDIA and Dell Local AI Hackathon. I will have access to a Dell Pro Max with Grace Blackwell 10. It's a very particular type of hardware that we're going to be able to use. My goal is I want to prepare for this hackathon. And what I want to do in preparation for this hackathon is to show you how I will learn out loud, how I will admit when I am wrong about doing something in this process. And I am going to focus on aligning with other humans rather than going too crazy with AI. The reason I'm doing this is because last Saturday I got a chance to meet one of my personal heroes, Professor Jung Shu Kim. You may see him on YouTube as Predictive History, teaching game theory. And I watched his lecture series on the great books, civilization, as well as what many people know Professor Jung through a very special and timely series called, I think it may have been called the Secrets of Evil or something like that. It was something truly amazing that helped many of us in America understand the Iran war and understand what would unfold, as we've seen that our cost of living has inflated quite dramatically. Um, so, just kind of keeping that in mind, I wanted to use that inspiration to think about how I will take those learnings into what I do for my day to day work. Currently in my day-to-day work, I am doing some developer relations for an AI lab, Prism ML, and Prism ML focuses on getting intelligence everywhere. And that happens through local AI. So I want to participate in a hackathon that is being hosted by my friend Somya Gupta. He's a venture scout at eWar. eWar is a venture capital firm based in Europe, focused on finding people who want to build something over the course of the next 10 years. So I really like that idea of people who think in decades. I always, kind of find myself as someone who aligns with long time horizons. Additionally, the bonsai model of families has been shipping a large number of models. Uh, Most recently, there was a series of models in their 27 billion parameter class, both at 1-bit and ternary. And what really makes this quite special is that if you have an iPhone 15 or better, you would be able to run this level of intelligence on your phone. This matters a lot because all of the Y Combinator companies that were building last year were predominantly built on on a reasonably priced model, which is Sonnet 4.5. And now everyone in the world has access to running that level of intelligence on your phone. This means that we can solve many problems in civilization, but it requires us to get intelligence everywhere where we need it, and we need to coordinate on using it for the right use cases. For the NVIDIA Dell Hackathon, this is going to specifically be, um, focusing on an always on business agent that can run locally. And so, with different types of AI agents, as you see on the board, there are various agent types, and I will just zoom in on this briefly so that you can see this a little bit better. So we will see that, there's agent types, which is like you can have an ambient agent, meaning it's always on. That's what they're requesting. But a lot of the features that we get benefit from is not just a single turn, it happens with a very long loop. And so when we have a long loop or a long horizon, that is a deep agent. LangChain made a very good open framework called Deep Agents, which is based on the architecture of Claude Code, which was released last year, which is one of the most important moments in AI history right now in terms of civilization level adoption, because now we're beginning to have agents who can confidently do economically valuable tasks for us. And then we have number three, which is when an agent has the ability to awaken itself. And I think this needs to be mentioned with the next section, which is it's not it's not just about an agent, it's about the plurality of them. And for plurality, we then need to know, where are they going to run? Currently, if you have a bunch of different agents running in various data centers, now you have an issue of a lot of foreign agents who can come into a system where you are quite vulnerable. This paradigm changes dramatically with local AI. Local AI means everything is happening on your network. If you are running local AI with an open model, even when a mistake happens, because you have access to the model and that model's weights are open, you can reproduce the situation because everything happened in your system. You can trace everything. And then you would be able to go inspect how which weights were being activated at that moment in time, and then you can go reason about why this occurred, and you can come to an actual judgment on what's going on. So this is really important, for governance. And governance is the biggest blocker to adoption, just because there's too many moving pieces, there's too much risk for a lot of established companies to adopt AI successfully. So for the hackathon, we have a limitation. The limitation is that we have to use OpenClaw or NVIDIA's NemoClaw, as well as something called OpenShell. And so another thing that is noted is that there can be no remote LLM or any API calls in the agent's runtime path. And so this is something that we will need to architect of what is going to happen kind of like at training time, but really the agent's runtime path, you know, it's part of the application's path as well. And so like this is where you need to have like strong delineation of um of where things are going to be. And that's like another reason why OpenShell matters here, because it has a very particular type of architecture. We I can pull this up briefly from the actual NVIDIA website about this. So what I'll do is, here we have NVIDIA's NemoClaw. This enables us to deploy more secure, always-on autonomous agents for real-world workflows with open blueprints. We can see that these blueprints, they include this agent toolkit, and this agent toolkit also has components inside of it. The components that they highlight are OpenShell, Nemotron, and Nemo. OpenShell is a runtime policy, or OpenShell is used for runtime policy controls. Nemotron is is being positioned as a frontier model. And then we have Nemo, which is for specialization and optimization. And so each of these, they're thinking, are going to be important for us. And for the time being, for the purpose of the hackathon, we're just going to take a look at, this is a runtime for autonomous agents. So run any agent more safely, shape its access, not its capabilities. Um, so here we go. So now governance, remember I said this was like one of the most important things to adopt. This is like, what do they have access to? The other thing is being agnostic to the host. This should be able to run, ideally on any type of device, because interoperability matters a lot. Next is self-evolving safety. Agents can learn new skills and install packages without risking the system's integrity. So the way that the architecture works is that there's policy authoring and signing that gets passed into a gateway for OpenShell, and then that will be routed into different sandboxes. And then that sandbox is what is going to hold a coding agent. Another sandbox can hold an orchestrator agent, and another sandbox can hold a specialized agent with skills and tools. And the idea here is that your specialized agent is where your domain is going to be. So there's going to be a lot of economic value in the long tail here with skills and tool use. Each of the sandboxes is programmable, and it's individualized. So it's, it follows that principle of kind of like kind of least access, right? Because that's the goal here. Then there's a level for granularity. So like the what, where, and how. We would just have like a simple framework for defining that so that we don't get bamboozled by it later in the software development lifecycle. And then having a gateway. So the gateway being like, hey, you're beyond our borders right now. You're going to pass the message in. We'll take care of it, and then we'll pass it back out to you. This is this is very important, and it requires us to understand drawing boundaries. So I just went through the OpenShell architecture. Um, so coming back to our application, I had to think about, well, what is it that I want to do? And so my idea for the hackathon is that we want to create something that's going to create a lot of business value. And so in the NVIDIA ecosystem, there's a lot of people who are building digital twins. So what I'm going to do is like, this is how I went about thinking about what should we do. So inside of the NVIDIA use cases, I wanted to click on see all use cases, and I wanted to see like, okay, like this is the most valuable company in the world. What are they thinking about? All right, so number one is algorithmic trading. Okay, there's a lot of money there, duh. Catalog enrichment being like, okay, so if I do consumer packaged goods, if I'm using LLMs, computer vision, and video analytics, I'd be able to I would be able to enrich my catalog, and I probably have like a lot of videos, a lot of images, and a lot of data that I can process and annotate potentially. And then put that into a lot of places where things are just kind of like missing, having more information. Then again, we see consumer packaged goods, which is having an AI shopping assistant. We see robot safety. We see synthetic data generation for agentic AI. I think this is a very big one right here. Then we see cybersecurity, operational technology, cybersecurity for risk mitigation, um, AI agents for healthcare contact centers. And so that can be inbound. And so my idea here is that, okay, there's a lot of inbound calls, but what about when you need to make an outbound call to a patient? And the issue is that they may not answer. And so, what I'm going to say is that, right now we have call centers, and then there's inbound uh, call in. And so, the customer's live. Outbound, your big issue is that what if they don't pick up? Or a number of different things. You just need to give them information. You need to get a heartbeat, or you need to collect unstructured observations, right? Like you need to, so in healthcare specifically, when a patient is discharged, right? And so what I'm going to say is the problem space for a digital twin is that patient discharge, but then you need to monitor them. How can you do that? Well, you can't do that with inbound. Inbound, they would have to call you. Outbound, you need to check in on them. You need to have a touch point to do that. But now you have an issue of, oh, like, what if they don't pick up my call? What if they're not motivated? Or what if there's a specialty situation that makes this hard? And so the specialty situation that makes this hard is what happens when the person has a problem with substance abuse? What happens if they have a mental health challenge? What I want to propose is that using local AI, I will clone my own voice. And by cloning my own voice, what I want to do is I want to create something where I'm calling myself to check in on myself as my ideal self. And I'm going to do this with memory so that I'm hearing myself with a few of my own memories, but guided. We're going to be guided, right? And what are we guided by? Well, remember the specialized agent uses skills, tools, and will give it memories. And that just by using these three things, I will be able to get dramatically better health outcomes for these specific use cases of substance abuse, for mental health, and so much more, even including basic personal improvement. That's my challenge for today. So, the first step in this challenge is going to be, so I'm going to remove this. Let's do, yeah, that. So now let's go ahead and let's do voice cloning. Watch me clone my voice live. So I have another computer set up right here, and I also have my phone. This is an iPhone 11. So what I'm going to do is I'm going to record about 70 iterations of me saying things so that I can train my voice on the AI. And then what I will do, as I mentioned before, is that with voice cloning, I'm going to get voice samples. Then I'm going to have data annotations using Bonsai 27B. Okay. So what I will now do is I'm going to unlock my phone. And so I have this set up, and I have a super duper simple setup where I'm just going to record a few annotations. Hi, it's your check-in call. How are you doing? Good morning. I just wanted to see how you're settling into the day. And then I'm going to have to retake that one because I stuttered. Good, good morning. I just wanted to see how you're settling into the day. Hello, it's me again. I've been thinking about you since we last talked. That one's going to be like a her type of situation, I feel. Hi there. Is now still a good time to talk for a few minutes? It's good to catch you. How has your morning been so far? I wanted to check in and see how you're feeling today. How have you been sleeping this week? Have you managed to eat something this morning? How's your energy been the last couple of days? Did you get outside at all yesterday? Has anyone stopped by to see you recently? Are you keeping up with your medication all right? How are you feeling in yourself today, honestly? Is there anything that's been worrying you? What's felt good this week, even if it was small? Last time we spoke, you mentioned Emily's recital was coming up. You told me on Tuesday that your knee had been bothering you. When we talked on Saturday, you said you'd been sleeping better. You mentioned your son was going to call over the weekend. I remember you said the garden was starting to come back. That sounds like it's been weighing on you. I'm glad you told me that. That does sound like a few hard days. I have to redo that one. That does sound like a hard few days. It makes sense that you'd feel tired after all that. I can hear that you're doing your best with it. That's a lot to carry on your own. It sounds like you've had more on your plate than usual. I want to make sure your care team knows about that. That does sound like something we shouldn't leave alone. I'm a little concerned about the dizziness you're describing. I'm a little concerned about the dizziness you're describing. Would it be all right if I pass that along to your nurse? Let's make sure someone checks in on you properly today. I'm not a doctor, but I don't think that should wait. You don't have to figure it all out today. I'll check in with you again soon. Thank you for talking with me. It was good to hear you. Take it gently for the rest of the day. I'll let you get back to your afternoon. You did the right thing telling me about this. Rest if you can, and we'll talk again soon. All right. That was about 40 of those. I'm going to take a quick break and look at the stream just so that I want to just like double check what's going on. All right. Awesome. All right. Whew, that was like a lot to do just there. And I do have to say, like, wow, like a lot of those hit pretty hard. And not only that, but then when I go to hear that back in my own voice and I hear that empathy, oh boy, I think that one's gonna kinda hit like a gut punch, seriously. So, yeah, I'm just gonna take probably I'm gonna take 10 deep breaths briefly so that I can maintain my energy and then run it into the end zone and then run a training loop on top of this. Currently, I'm collecting voice samples. These voice samples will then be annotated using Bonsai 27B along with a mixture of other models, keeping in mind that Bonsai 27B doesn't have the ability to process audio. um, we will have to figure out different ways to annotate data instead. So that's going to be one of the things that I'm going to consider is how are we going to label the data, and that the label data will then be used with the original data, and then we'll use that to fine tune, and we'll see if we can get something that gets close to my own voice. Now, remember, the goal that we're going for is when a patient discharges, you need to monitor them, or you talk to someone and they're going through something. We need to collect unstructured observations, handle escalations, and do a lot of things that are in the chain. These are things that, there's serious work to do. This is the type of work that, if you want to get it done effectively and properly, it's realistically going to cost $20 to $35 an hour. And you have thousands of people to do this with, and a human can only talk to one human at once. However, if you can have a strong outbound system, and then, once people opt in to saying, yeah, I actually do want to talk to someone, I do want to consent, and it's going to be this type of conversation, or maybe it's just going to be basic administration, you can route them effectively. If we can route people effectively, then we can deliver dramatically better care. Okay. So that's my goal. I want to deliver dramatically better care for everyone in the world, but starting with my own community. I'm going to come back to the training loop and collect voice samples. Okay. So before I do that, I'm going to take a few deep breaths just because this is a tremendous amount of work. And so to do this consciously, to do this correctly, you have to be you have to be the human in the loop, and you have to be a professional of knowing how to boom, just be able to run things through the end zone. So all right. So let's get back into it. Oh no. I'm so sorry to hear that. That's wonderful. I'm really glad. Take your time. There's no rush at all. That must have been frightening. I understand. It's all right. Are you sure you're okay? You sound a bit tired. That's a real accomplishment, and I hope you're proud of it. Hmm. Tell me more about that. Of course. That makes complete sense. Did you sleep all right or were you up in the night? I'll redo that one. Did you sleep all right or were you up in the night? Would you rather talk about something else? Is your daughter still coming on Thursday? Have you been able to get to the shops this weekend? Do you want me to stay on the line a little longer? Was it the stairs again or something different this time? It's the 21st of August, a Thursday. You mentioned it started about 3 days ago. Your appointment is 2:15 on Monday. That was 1974, if I remember right. About 75%, they said. It's been 11 days since your last visit. 22, 37, 48, 59, 63. Dorothy, Margaret, Eleanor, Thomas, and Raymond. She's in Manchester now, near her sister. Dr. Okafor called about the results. It was St. Thomas's, over on the north side. The strengths of the 12th month surprised us. She asked for sixth. Oh, gotta redo that one. She asked for sixths and twelfths, which sounds awkward. Crisp text scrolled past the glimpsed screens. World thoughts, ninth breaths, and mixed depths. The rural juror judged the brewery's blueprint. "30 thieves thought they thrilled the throne." Please pass the fresh shrimp shells and thick sliced bread. I know it's not easy to talk about, and you don't have to go into detail, but I do want to understand how you've been. When you said that last week, I wasn't sure whether you meant the pain itself or the worry about it coming back. There's no right answer here, and honestly, whatever you tell me is going to be helpful for the people looking after you. If it turns out to be nothing at all, that's a good outcome, and nobody's going to mind that we checked. I'd rather ask twice and be a bit annoying than miss something that mattered to you. That's pretty hard hitting, I gotta say. Um, wow, wow. I've never participated in the training loop before, and I always thought that it was gonna be like totally robotic. It was gonna be like so remnant of like slavery. But of course I didn't know, and so I didn't, my imagination wasn't there. But now I've just done 79 iterations of providing voice samples, and a few things I noticed was that a few things that were programmed in were very close to the domain. But then what I noticed immediately after that was that there were a number of examples that tried to find patterns in how I was going to speak by creating some cases where it was like, oh, like everything starts with a T, or this is actually kind of hard to say. So, how would you say those harder things? And so, I kind of understand how the samples kind of like put together. And so now that's all recorded onto my machine. And so now, uh, say just recorded them all. All right. And so now what's going to happen is that we have to go through a training loop. So we've now collected, 79 little files, but the next step is going to be, how do we process the data inside of those files effectively? So that process is going to happen by way of it's going to happen by way of labeling data. So we're going to say, what type of data do we have? Then, given our resources, whether I'm going to have a human label the data or whether I'm going to have a machine label the data. The machine can label the data either deterministically, being done using code, or you can use a technique called using an LLM as a judge. The technique that we will use for today is using an LLM as a judge, as well as just processing the data, for synthetic data generation. We'll use the Bonsai 27 billion parameter model in its ternary format to do this for us. We'll do this because this will enable us to train quite quickly entirely for free. Previously, I ran a training loop for 34 minutes to generate synthetic data to label and fine tune. If I was going to try to do that, using someone else's cloud, that would cost me roughly $120 to run an operation like that. Not to mention all of the other parts of the infrastructure that are going to need to be there. So it becomes a very expensive process, and it usually takes weeks, if not months, of coordination. And as we know in the AI landscape, we are very nimble to the fact that anything can change at any moment. For that reason, doing things for a matter of like weeks or months before we can get to alignment is problematic. But now I see an opportunity, and within 34 minutes, I can train, and then I can get a checkpoint, which is a checkpoint is a filed up version of the model, the AI model just being an array of numbers. A checkpoint is going to be a versioned instance of that. And so then I can immediately test the checkpoint out and be like, okay, this is exactly what I wanted. And now I can move beyond just training into applying it. And when I apply it, I learn what happens in production. When I learn what happens in production based on user behavior, and then users will then want to tell me what they care about more. And then I can get to an alignment with the actual users. And then I know that this process is working. I have an effective training loop. Um, okay, mind. All right, unfreezing more. All right, so what I'm now going to do is, so I have 3 minutes and 40 seconds of audio that you watched me record. Those were 79 clips. They were roughly 2.8 seconds each. So they're all recorded and they have been transcripted as well. There's been no errors that have been flagged so far. Um, so then the next thing is that now I have a total of 1,094 clips because I have 620 clips of audio from doing these live streams. But the issue is that I'm literally like kind of lecturing to you right now. And that's not how a conversation is going to go for the application, but it is capturing my voice. But it's capturing my voice in a very particular instance, which is, I'm presenting on a whiteboard. I'm going to talk significantly different when I have a whiteboard behind me than if I'm with you, or especially if my intention is to connect with you. So that's why we went through the training process again after realizing that. Now we have 474 clips, which now about 43% of makes up about 43% of the total number of clips that we have. And so now I have those, and now I need to run a training loop against that. And so the last run moved only 1% of weights with 30% of the model trainable. Um, since the training runs that I ran seemed similar enough last time around, the adaptation depth looked like a co-limiter alongside the data. So this runs trains of 10 of 22 blocks instead of 6, which raises the optimizer floor. So right now, I think, this is just trying to help me think about how much overhead I currently have on this node to run training, because training is computationally expensive. And now also runtime is computationally expensive because we want to also have generative AI at runtime. And we realize that runtime has a lot of our context too. So we want a highly capable foundation model that can run performantly at runtime. And then also, so it's two sides of the coin: training and inference. Um, all right, so it's expecting there's going to be 1,000 steps. There's going to be 15 epochs. It'll take roughly 50 minutes, and it'll do 8 checkpoints. It will then try to judge itself. Okay. All right, amazing. So now we're going to go through that training loop. So my next job in preparing for the hackathon is reasoning about the NVIDIA architecture. And now my goal with the NVIDIA architecture, so my goal with this NVIDIA architecture is I need to create a use case for something that's going to be always on. So an always on outbound caller, always on outbound caller. And really it's going to be like a case manager digital twin. That's like ultimately what I want to be able to like get to, is having some type of architecture to do that. This is like a monetizable problem. I don't want to get too lost in like the business, but like you got to remember, one of the most important parts of alignment is having business value. That's why the benchmarks are always considering what must be done. What must be done when we're applying AI. It needs to have some economic impact. Otherwise, people are just going to quit on it. So we need to use our architecture So there's OpenClaw, then we have Nemo Claw. So I'm going to evaluate these. Then I'm going to take a look at OpenShell, which is going to be the runtime sandbox. Then next up, we're going to have Nemo, skills and tools. So this is going to be my optimal architecture because it's coming directly from NVIDIA. And so if I can use these building blocks, then I can get to this outcome because I don't have to use all my knowledge on reinventing the wheel. That is why NVIDIA is telling us they're giving us these blueprints. So the next thing I need to do while this training is occurring is I need to look at the canonical guide. So this is the canonical guide from NVIDIA. AI agents for healthcare contact center. So this is for workloads that are for conversational neurolinguistic programming, which is what we are looking to do, as well as using, generative AI and large language models alongside of this. So the business goal that NVIDIA is saying is that they're looking for ROI. So let's understand how this ROI is going to be measured. What are they going to measure here? So currently, these tasks include scheduling appointments, collecting billing, insurance information, and managing patient inquiries. Additionally, AI virtual assistants offer services like telehealth chatbots for patient advice, automated follow ups to ensure ongoing care, reminders for medication refills, and efficient routing of patients to appropriate services. So this is exactly what we want to look for. And so this is important in NVIDIA's AI enterprise. So that's another big thing is that this is for NVIDIA's AI enterprise. However, so we have AI agents for healthcare contact center looking for ROI in the AI enterprise, but I'm now going to pull up the Dell GB10. So this is Dell Pro Max with GB10. This is a NVIDIA GB10 Gray CPU. A lot of different ways to describe this. It's like a little bit of a mouthful. It's just like a little too hard to say, honestly. But let's try to understand what this is comparable to. And so when I take a look at the specifications, so I want to get to a spec card because I want to know what workloads can be supported on here. And so a lot of times you can find signal inside of here. So, hey, this is great for local AI. Great, amazing. I know it's good for local AI, but it's not saying it's good for enterprise AI. And this is a super expensive machine. So that's kind of a little bit where we're immediately going to be like, all right, well, how do I think about that? Right? So that's super important. Another thing is that, using this machine tomorrow, there's going to be a cold start problem with the machine because we're going to have to figure out how to use it, how to get it up and running, and how to give it everything that I need. I'm going to need to take a look at what ports it has available. So let's take a look. It has USB-C. I can transfer at 20 gigabytes per second. So if I have things in an external hard drive, I have that. If I have a local area network, I would be able to connect into the machine. I can use HDMI and I can connect into something. So that's super important. And then I actually don't know what these are. So that's important. Let's look at the specifications. So there's also storage. And so I don't know if I'm getting a terabyte of storage or if I'm getting 4 terabytes of storage. So that's something worth considering. Then there's a power cord. So this is going to use a lot of energy. Wi-Fi and Bluetooth, power supply 280 watts. So this is why a lot of people are talking about this measurement of intelligence per watt, because like this is a lot of energy. Okay. All right, so this is 128 gigs of unified memory. So this is a very important paradigm here. Um, but another thing to think about is, well, what AI is going to fit onto here? And so if I go to local.ai, what we're going to end up seeing is that in this family class, we're going to note that the best model that's going to run on here is Quen 3.8, 27 billion parameters. And when we take a look at what this is going to be capable of doing, we need to understand the benchmarks of what we're expecting to see here, as well as what speed we're going to expect as well. Because we may want to use a mixture of different models, this plus some smaller models if we want to try to get some speed. What I'll now do is I'm going to come to the model card on Hugging Face. So what we're going to do is we're going to take a look at the highlights. When I go to read the model card, I'm going to see the core capabilities are going to be professional work, research, and long horizon agentic tasks. That's what a lot of people care about, because then you have a worker. And if a worker can run on this machine, that's pretty phenomenal. And I think that's a big thing, is that, tomorrow when we do the hackathon, if it's like, oh, hey, like I have this set up where my worker is going to awaken itself, make a phone call, talk to the patient, then route things accordingly, and then connect into my systems and do the admin work for my people, so that then I can really effectively triage. And when I effectively triage, I get better resource management. Immediately, I love this as a promise. Now let's dig deeper into it. So we have agent execution, so stronger autonomous planning and better handling of environment feedback. So more reliable end-to-end task completion. So that matters a lot. Downstream compatibility. So like it's going to work where I'm already using things. So I think that's important. Vision language understanding. So it's going to natively support image and video understanding, from STEM diagrams and documents to hour scale videos. That's super, super, super good. This is a claim that I would want to test quite a bit. What's missing here is audio. And we'll get into audio as a data type in the future, but probably not for today. Now for the model type. This is a causal language model with vision encoder. That's interesting. Have you heard of a causal language model? I've heard of a large language model. I haven't heard of a causal language model before, though. So that's unique. Then the training stage, hidden dimensions, how many layers? There's 64 layers. Gated attention head, blah, 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 blah. All right, benchmark results. So let's take a look at how they're comparing. So they're trying to compare to both Muse, the superintelligence lab from Facebook, and saying, hey, like, we're similar size and we blow you out of the water. Then taking a look at Opus 4.6 Max. Now that's a very unique benchmark to pick, is like picking a model with its reasoning level, but I think that's a really good way to measure it. It would be good if you're going to say max to see what medium and low are as well, just because then, it leaves that as an open question. But this is pretty massive. So now, really, what we're saying is, well, what does Opus 4.6 represent? What does Opus 4.5 represent? Um, and now here's another thing. There's a new benchmark, Agent's Last Exam. And in Agent's Last Exam, it got this score. So this is something that I want to look into for Agent's Last Exam. So Agent's Last Exam is a pretty legit benchmark. Let's take a look at the leaderboard. And now we see they specifically wanted to see how Quen would do here. Quen is pretty mighty here. So let's understand what we just saw. And so this is Quen 3.8 Max. This is a much bigger model here, but Quen 3.8 27B is at 20% here. This is really significant because Codex is here at 30%. So this is really the little engine that could. So given that, I want to understand how this, like, I only really want to look at this one and I want to isolate this. But what just happened when I clicked on it was that it went away. Oh, because that's what it's, when you click on something, it hides it. I would have thought that, like, if you click on it, like, you'll get more information about it. But what I'll do is I'm gonna click through, like, this is the overall, but I'm gonna start keeping a track here. But this is the pass rate. Let's take a look at the score. So the score is 42.9. So that's interesting. And then to see both, if there's like any crazy deltas. No crazy deltas that, like, I immediately see, but I do see that, like, I see why it's coming before these. So that's unique. And then, like, the other thing is that, why is it saying like Claude Code Max below it, right? That's unique. I think this is saying what harness it's inside of. And so there's a harness, and then the harness has its own reasoning setting, maybe. Now let's take a look more. So in Linux-based tasks, Quen holds up to where it is. It actually holds up quite well up against Opus 5. So that's massive. And then also knowing Quen 3.8 beats Opus 5 on Linux. So I know for developer-based tasks, like, this is a really good selection here. So now near term, so it looks like what they are defining as a series of tasks that they're expecting to be potentially solvable today. So this is nice. We should take a look at what this benchmark specifically means, because this seems like a strong application. Because what is quite unique is that Opus 5 is not that far off from Quen 27B. So that's a unique observation. We'll take a look at, the scoring is similar, but the pass rate isn't enough. And now what I could surmise is that this would just be using a mixture of 3.8 Max and then 27B to be the sub-agent. And now we could conceivably beat Opus 5. And it's beating it on score, just not on pass rate. So this is where, using a mixture and kind of ganging up against Opus could really, like, supersede it. So that seems like a very unique blend worth trying. Is like Quen 3.8 Max as master agent, and then Quen 3.8 27B local as the sub agent, and see how that mixture would work together for that exam. Next up, we see the full spectrum. So this is across 50 industries. And so when we take a look at the full spectrum, what is amazing here is now Quen 3.8 27B is beating Opus 5 on the full industry benchmark. So that's pretty unique. And then the last exam. And in the last exam, Quen 3.8 27B, it's not passing enough. However, we see here 3.8 Max is passing. So again, we could see, wait a second, this is pretty massive that if you use these two things together, what would be possible? What could really be possible? So that's quite interesting. And now what we can see here is like, what's the cost? So the cost of running 3.8 Max here is like 217. Claude Code is too prohibitive at $3,851. Same runtime in terms of total amount of time. So that's quite unique. We do see a tremendous speed up in time with Fable and Fable downgrading to Opus whenever it decides to refuse. Quen 3.8 27B runs for 114 hours on the benchmark. Um, it has a great score, just not the best passing rate. And so this seems like, okay, this could be something that is pretty massive. Um, Now, the next thing is like, we have a leaderboard. There's traces as well inside of here. So let's see, best per task, apples to apples comparison. So this is going to be, looking at those two models. This is replaying a particular trace. Yeah, this is doing some very particular type of evaluations for specific industries. Then there's a task list of what the examples are, visual examples, and benchmark splits. So now we can start to see, like, okay, given where it's at, where could we expect it to go, given what it is, and then given where it's currently weak, where's the opportunity for training? All right, my training run set is still running, and I'm expecting that this is going to wrap up. Let's see. We'll see how much time it's going to take. All right. Streaming for about a good hour on a Friday morning, so that's always a great thing. My computer is computing, I'll tell you that though. My computer is computing. I'll have an answer to that in a second. So as I go to evaluate Quen, it's my job is going to be to understand this. And so the next thing I would need to do is I'll do agents. So this is where I'm going to use Google, and I'm going to say agents last exam Quen 3.8. So we'll take a look at what they're going to say about this. Um, well, they're showing it for the big model in here. I was looking for something different. Let's see. Let's see what the jump is here. Oh, this is a big jump. Yeah. Okay. So Quen 3.627B managed a 53.5 on this benchmark, which is respectable. It's usable for some tasks. 27B hits 61.7. So it surpasses Quen 3.7 plus, and it also beats Opus 4.6 Max. Um, so Deep Sui, aha. So SweBench Pro shows steady mastery. Deep Sui 1.1 reveals that it jumps quite a bit on this benchmark. And so, you know, sustained reasoning across multiple files, understanding of build systems, and the ability to trace execution paths through complex dependency graphs. So, um, I think that that is a helpful benchmark because now, you know, that definitely shows like a lot of really good reasoning capabilities and like valuable work, and the value being like, everything is dependent on each other. So if you can start using it there, where could it be applied? They have their own bench, agentic intelligence, long horizon office work. So that would be through Cowork Bench. And so Cowork Bench, then this is professional task execution. Computer use. Yeah, this is a big leap. I think computer use matters a lot. So now this gives me an idea of like where to try to go after certain things. I have like a slight intuition on on a few of these things. I'm also seeing a few things on like the benchmark. Let's see. So very big context windows, long timeouts, maximum number of tokens. So the focus is long horizon reasoning. So that's what they're looking to do, long horizon reasoning. And so this is the thing is like, you know, a lot of specialized infrastructure is a lot of specialized infrastructure is on H100s. And then there's consumer level devices like the RTX 4000 class software, which could run this, if this was quantized effectively. And so that's the goal of the Banzai model of families is to, take this massive innovation and to bring it to consumer grade hardware. on the edge to make intelligence accessible everywhere. So we just took a look at the benchmark. We have our training run, which is going. And the next thing that I want to do is we have NVIDIA AI agents for healthcare contact center. And keeping in mind, this is the reference architecture for the enterprise. The use case just provides like, okay, I now need to go to a blueprint for digital human health. And then I'm going to need to take a look at what models are they using. So remember before I said there's different types of agents. This is using deep agents. They're saying deep agents is going to be accelerated by the Nemo agent toolkit so that we can self-host. The architecture is that you could have a user or an agent that's going to send a query and get a response back. It has the ability to upload data, has the ability to connect to data sources. It has a knowledge layer for memories, which can be done through RAG, through search. Then it has a deep researcher, which can do long horizon reasoning and then come back with knowledge-based tasks. So this seems like this is going to be a pretty phenomenal example of what's going to be possible. Now for the models, this is being powered by Nemotron, um, 3.5 Lightning 30B. So that's going to be used for intent classification and in shallow search. So that's just used for search. Then we have Nemotron 3 Ultra 550B. Womp womp womp. We can't deploy that. We can't use that. It's too big for this machine. So we have a problem here because now for clarification and deep research, it's probably not going to happen on this size of machine. So what's going to need to happen is we're going to need to dramatically simplify what the architecture is, because what we could do is we can try to have only a threshold of complexity that we can go for with a small 27 or 30 billion parameter model, and then use just the basic capabilities and different agent personalities like a planner, an orchestrator, a researcher, and a writer that can work together, that can access skills and a shared execution runtime. And so if they can do that and then report progress, then we can just do some shallow checking, then we can do some refined checking, and then just kind of like a double check, do things just a little bit deeper, and come back on certain types of situations. So the architecture is still something that I know that we can definitely lift. And then keeping in mind, there's a lot of parts of this blueprint that just won't work. So parts of the blueprint that just won't work, as a reminder, are going to be like there can be no API calls in the agent's runtime pathway. So that really kills a lot of the use case for, you know, for using OpenShell and for using Nemo. So we'll talk about that. But I think, OpenShell is going to have a lot of information about that. So we'll review the Nemo agent toolkit, the Nemo guardrails, and the blueprints that are available. We'll bring all of this down into something that's going to work on local AI as a next step. And just as an update on where we're doing with regards to training the voice model that we're going to use for our outbound caller. We currently have 5 checkpoints out of 8 checkpoints in our training loop right now. We're expecting in roughly 11 minutes that this process will complete itself. And so a few things that we're kind of looking at right now is the loss value, which, currently we're oscillating somewhere between 0.72 and 0.78. For the drift in our weights, I need to understand a little bit more about how that's measured. So now I know, like, okay, why would I measure that? What is that going to give me an idea of? Then I'm taking a look at memory, how much memory is being used, if any of the steps were skipped, what's the speed. So it's going through each step in the training loop at 2.39 seconds per step. So let's see. So I think when we're measuring weight drift, there's something about measuring a saturation pattern, which is going to be measured um, by cosine decay winds. So again, these are things I'm going to have to get a much stronger understanding of, but I think this all ties back into gradient descent. And so this is, I guess, kind of looking to smoothen out the waves because the gradients are spiky, getting larger. They're not settling just yet. Um, okay. It could have been that it oversampled, and so this is trying to go through this process. Remain steady. The demo path is unchanged. Drift is saturating, the same flattening I saw last run as cosine decay wins the step size down. The final 280 steps will contribute little, so 1,000 is probably more than needed. Okay, so hopefully that doesn't overfit it to anything. Um, all right, great. So I'm going to be able to get two different versions of this in a second. So what I would say is this could be a great time for a break. What I'll do is probably get something onto the screen that we can see. Got the GitHub page for Nemo, which is the agent toolkit that we will use. And so a lot of the things that I naturally do that I hand roll a lot, like profiling a workflow, having observability, these are things that are going to be baked in. Be able to click in, see how observability is happening right now. Oh, look at this right here. So I can observe with Arise, with Galileo, with Dynatrace, with Langsmith, with literally anything. With weights and biases, they have a product called Weave. Phoenix, which is like open source from Arise as well. Deterministic identifiers and timestamps. All right, but yeah, basically this is going to just fit into the open telemetry framework that is used by any of these. So that's awesome. Um, but I guess that's something I'll have to like configure as I do all of that stuff. Hello world, blah, 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 blah. And there's also a roadmap of what to expect inside of here. So that'll be helpful for me to know. All right. So this is a perfect time for a little break from me. So put myself on mute briefly. All right. Oh, bless me. So we're now in this kind of final part of the process um, of training. We're expecting that that original batch that we began with is going to finish training on the second machine that I have. I'm expecting probably like another 5 minutes here, but I want to get a quick report on where we're at. So yeah, now we're at step 920. The drift is now completely flat. 1,000 steps was more than the configuration can use. 600 would have gotten to the same place in 40% of the time. And then it's going to compare all the different checkpoints that we have. So we'll now get to start listening to how these performed. We'll pick the best one. Okay. While I wait for the final 3 minutes of this task, is so this is the environment that NVIDIA is saying that we will be able to just kind of like place our skills and tools if I were to use something like this. So it adds intelligence to AI agents across any framework, enhancing speed, accuracy, and decision making through enterprise grade instrumentation, observability, and continuous learning. The key features: AI coding agent skills, use focus Nemo agent toolkit skills to give coding agents task specific guidance for building, evaluating, optimizing, and observing workflows. Agent performance primitives is a graph based agent framework. So I guess the same thing as LangGraph. Public plugin API for third party tools. Langsmith native integration, observe end to end agent execution. You know, this is such a fun. It's a it's a little bit of a, I don't really know what to call it, but it's a little bit of a stretch in terms of what we originally saw. So I know that people typically don't like that. Well, I'll look deeper into the NVIDIA ecosystem. I'll probably do like a happy hour tonight for looking at that. This morning, you know, the important part for this morning was we want an always on outbound caller. I think like the most important thing is having like a voice demo. Being able to have a voice demo, being able to clone your own voice, have that digital twin, and then have like a framework for being able to do that locally on local AI. I think that matters a lot. Um, all right. All right. Generating samples. So it's now going to generate what it thinks my voice is going to sound like. And so I'm going to listen to them, and you'll probably be able to hear it too. We'll see how well it's gonna carry it. Um, so let's see. So one thing is like it's creating these checkpoints during the training loop because training is very expensive, and then it's partitioning, being like, hey, like after a certain point, I didn't really improve myself. And so, it could just be that now, like, I'm going to be overtrained in the wrong direction. So then I'm going to capture a checkpoint that, um, and now it's going to try to decide who the champion is. So let's see. So, boom. I want to hear this. I just wanted to check in and see how you are doing today. Ugh. I just wanted to check in and see how you are doing today. No. We're going to check the checkpoint from 750 and then 1000. I just wanted to check in and see how you are doing today. Too much. Let's see. I'm going to check 1000 real quick. I just wanted to check in and see how you are doing today. And then we have at 500. I just wanted to check in and see how you are doing today. Okay, now, I mean, it's close enough to my voice, but not perfect. I just wanted to check in and see how you are doing today. All right, so I just picked a winner. Checkpoint 600 was the winner. So I do think that so I've now told it, hey, we now have a winner of like what is working. So then the next thing I want to do, if I think I have a winner, okay. Oh. Hmm. Wait, hold on. Where was the new training? My ears against this. Let's hear this. I just wanted to check in and see how you are doing today. I think that's where it screwed up there. Now, if I check 500. I just wanted to check in and see how you are doing today. Let's see, okay, that's not it. I just wanted to check in and see how you are doing today. Yeah, when it goes how, I think it doesn't really, I mean, I say how. But I think maybe it could just be like where it picked up the word. Let's see, 625. Nope, it's not 625. So it looks like that training run didn't do anything. So I don't know why that's the case, but it is what it is. I do want to hear. Oh, it doesn't exist. That's why it fails. You declined the command that would have generated 625. Well, I just wanted to check in and see how you are doing today. I want to hear the current winner, which is, oh, that's just an eval. And then eval 600. I just wanted to check in and see how you are doing today. Compare that with this. I just wanted to check in and see how you are doing today. Yeah, just with that how, though, that how is just so bad. I just wanted to check in and see how you are doing today. And then, like, it really gets on that how. So let's see, 250. I just wanted to check in and see how you are doing today. So now what I'm doing is like I've now found two checkpoints. So I think this is an important part to do is like, so in the training loop, remember we're in the training loop and I wanted to use Bonsai 27B for labeling data. And then what I ended up seeing was that we had these checkpoints in training. And so I had a checkpoint at like step 250 that I thought like, you know, beat the how problem because there was this like I was running into this problem where it was like how so I didn't really like that. So now at the middle point between the two checkpoints, because then there was another checkpoint 500 and it was assuming that 625 was kind of like uh, best in numbers. This one was kind of like where it begins to flatten. So now what I'm doing is I made a new checkpoint at 375 to see what gets captured here. We're going to listen to that one briefly. I just wanted to check in and see how you are doing today. Okay, that's not bad. I just wanted to check in and see how you are doing today. So now I'm going to give it feedback in between the checkpoints. But what I just did was like, this was kind of basically we set up some checkpoints and then we evaluated each. And then now what we can do is like, we just use the basic binary search where I was like, this one was the best because I'm specifically seeing an error problem in how I say how. So now I'm clustering like, okay, well, the reason was because of how I said how. That's why I'm grading 250 as my best checkpoint. 500, I'm saying flattens. So then at the middle point between 250 and 500, which is 375, I got the best one that I heard so far. And so now that means that realistically, between 575 or 375 and 500, we could find another middle point, which would be, you know, now we have to find what that ideal middle point is going to be, which I'm guessing it could be like kind of 438.5, could be some type of number around here. So that could be important to say, okay, well, is 438 better than 375? And if it's a no, or if it's a yes, then we can get to, okay, this is where the problem is. So that's one thing that we could do. Um, okay. So the contributed nothing to the final decision. Cosine rated every checkpoint tie. So there's ties and checkpoints on grading them. Optimum is 375. Degrades after that. Duplicate file oversampling. So document the oversampling issue. Use 375 and return to original loop. All right, great. So now I have successfully cloned my voice to a degree for this outbound caller. I'll now need to focus on having the correct. I'll now need to focus on having the correct runtime logic for the agent to have skills and tool use for it to be valuable, and then ensure that we stay in the memory overhead of the Grace Blackwell 10. If we can do that, then I know that we will be able to succeed for the hackathon. So you just watched me in real time. In real time, what I just did was I prepared for the hackathon. And what I did was I learned out loud. I admitted when I was wrong about certain things or when my AI was wrong. And I focused on trying to align with other people, not getting too lost in the sauce with AI, just using basic principles, basic Google search, um, not having too strong of any emotion anywhere. And that's been helpful. So I will probably do another live stream on this later today as I prepare for this, and I'll see you in the next one.